Thanks again for joining today's webinar. My name is Abdul Isi. I'm an engineered technical sales engineer at Antech Controls. My focus at Antech Controls is helping our sales and customer base with technical guidance and knowledge in critical space applications. For today's webinar, we are going to be focusing on room pressurization solutions in critical spaces. Room pressurization solutions will primarily be focused in applications such as laboratories, hospitals, and pharmacies. In these applications, it is critical to maintain both safety for the occupants within the space and the rest of the building. Today's course will review the requirements for room pressurization and space temperature control in each of these different types of critical spaces. The learning objectives for today include identifying the requirements for proper space pressurization, being able to distinguish between both a negatively and positively pressurized space, being able to show an understanding of the different methods for performing space temperature control, being able to show an understanding of the different airflow control devices and their applications in different types of critical spaces, and lastly, being able to correctly select and lay out a room pressure control strategy for critical spaces. The agenda for today will also include covering the applications for both laboratory, healthcare, and compounding pharmacies, discussing different room pressure control strategies and methodology, and then finally discussing some design considerations, including temperature control, airflow control, and selecting the correct either room pressure measurement, monitoring, or control strategy for these critical spaces. Standards that we're going to be referencing in today's presentations include ANSI Z9.5, ASHRAE Laboratory Design Guide, USP 797, and ASHRAE 170. Before covering the applications, it is important to understand the background for room pressurization. In essence, room pressurization is just the directionality of air movement going from clean to less clean spaces. This is done by building up a difference between your supply and exhaust airflow, which helps create that pressurization. Now, the magnitude of pressurization built up in these spaces can depend on a couple of factors. This includes the magnitude difference between your total supply air coming into your space and your total exhaust air leaving your space. Room leakage can also affect your room pressurization, local construction practices, the ceiling type selected, and lastly, your door selection or ceiling type. Now, the graph shown here on the right does a really great job visually demonstrating the effect that room leakage and your difference or that magnitude of difference between the supply and exhaust and how that can affect your pressurization. So as you can see on this graph here, if you have a very small room leakage, 0.1 square foot, you only require a very small difference in airflow between your supply and exhaust to build up your pressurization. The problem you can see here though is due to how small that difference of airflow is, minor changes can result in large fluctuations in that pressurization. On the opposite end though, if you have a space that has a very large leakage or a very large room leakage, you're going to need to have a very large difference of airflow in order to build up towards that same pressurization. So ideally, you don't necessarily want to have a room that's extremely tightly sealed where small difference in airflows can result in large changes in pressurization. But on the other end, you don't want to have a room that's so leaky where a large magnitude difference of airflow is needed in order to build up that same pressurization. Operating somewhere there in that mid-range ideally would be best case scenario. So with that laying the groundwork for us and understanding how room pressurization can be built and utilized, we can now go ahead and cover some of these critical space applications. The first application we're going to be covering here today is chemical laboratories. Chemical laboratories are spaces equipped for scientific experimentation, research, or education, typically utilizing airborne chemicals that can be harmful to humans if exposed. Types of chemical laboratories here can include synthesis labs. So these are spaces using organic or inorganic reactions for a wide variety of chemicals. We also have teaching laboratories, which are similar to synthesis labs, but requires the ability to accommodate for large groups. So typically for teaching labs, we're going to want to try to have an open line of sight so instructors can see and potentially prevent hazards occurring while these large groups are utilizing this space. Other types of laboratories we can see here are biological laboratories or BSL type labs. These are laboratories conducting experiments for research on living organisms, which can have a wide variety of hazards involved. So these spaces, depending on the type of biological lab it is, may require very specialized equipment like a laminar flow hood. Additionally, we also have hospital clinical laboratories, which are typically facilitating testing for specimens associated with patient care. So when we do focus on laboratories as a critical space application, one of the key driving factors for laboratories are going to be the fume hoods. So there are two main types of fume hoods we're going to talk about here today. The first type of fume hood is going to be open bypass fume hoods, which are typically operating on a constant volume or a constant exhaust set point. The idea here is you have a louvered front panel at the top of the hood, so airflow has either a route to enter through the top of the hood or through the sash as it's raised up. Since the fume hood is constant volume, as your sash opens, it covers that louvered front panel, and air is able to open and enter through the sash, maintaining a constant target face velocity for containment. These types of fume hoods have been very, very common historically, but are now moving out of fashion due to the high energy demand required to maintain this hood at a constant volume set point. So the second type of fume hood we're going to talk about is closed bypass fume hoods or variable volume fume hoods. So the idea with variable volume fume hoods is as your sash opens, the exhaust air volume required will increase or decrease in order to maintain a constant face velocity set point. There may be an opening or small bypass in order to ensure the minimum volume of exhaust air is maintained while that sash is fully closed. These types of fume hoods can be designed as both a vertical, horizontal, or a combination sash fume hood. And these are definitely the more common types of fume hoods we see these days due to the fact that it is more energy efficient. When that fume hood sash is closed, we can minimize the exhaust air demand required while still maintaining containment and safety on that fume hood. The second application we're going to cover here today is isolation rooms. So isolation rooms are spaces that can aid in the prevention of spreading airborne infection to other patients, healthcare workers, and visitors, or from outsiders to a particular patient. There are a couple of different types of isolation rooms that you may see in practice. So the three types we have listed here are airborne infection isolation rooms, protective environment isolation rooms, and lastly, airborne infection isolation rooms with protective environments. So the first type of isolation room we're going to cover here is airborne infection isolation rooms. These are isolation rooms where a patient has a communicable disease. This can be a smallpox, influenza, etc. So the goal here is to minimize the spread of that communicable disease to other areas of the hospital, potentially infecting other healthcare workers, doctors, and nurses. So in order to prevent the spread of that communicable disease, the goal here is we're always going to ensure that we have air transfer going from the corridor of that isolation room into the isolation room itself. So in order to maintain that negative pressurization, we're going to ensure that we have less supply air coming into that space and we have more exhaust air leaving that space, helping us build that negative pressurization relative to the corridor. You will also typically see the bathroom be negatively pressurized in comparison to the isolation room in order to prevent any fumes from escaping that space. The second type of isolation room we're going to cover here is the protective environment isolation room. So these are isolation room spaces where a patient now has a compromised immune system and needs to be protected from potential less clean air in other areas of the hospital. So in order to protect this patient that has this compromised immune system, we're going to ensure that the airflow always transfers from our isolation room to our corridor. So in this case, we want to have a positive pressurization. We want to ensure we have more supply air coming into that isolation room compared to exhaust air leaving that space. The last type of isolation room we're going to cover here is the airborne infection isolation room with that protective environment. So this is an isolation room where the patient may have both a communicable disease, but is also in a state where they have a compromised immune system. A relevant example to highlight here could potentially be a patient who's been exposed to nuclear radiation, where in this sense, they're both potentially communicable with the radiation, but also have an extremely compromised immune system as their body tries to fight that radiation. So the idea here with this type of space is we're going to try to utilize an anteroom to sanitize the airflow between both the corridor and the isolation room to help further minimize germs before flowing back from the corridor or to the room in that sense. So a space like this can really help protect both the patient and the rest of the hospital with this additional anteroom. Now, with all of these applications, with all of these isolation room applications we covered, you will also typically see pressure monitoring utilized to give visual indication that we are maintaining these pressurization targets. The next application we're going to cover here is operating rooms. So these are, again, types of spaces in the hospital where we're carrying out a surgical procedure in a clean environment. Now, again, these can be your very minor, quick procedures, all the way up to your multi-hour, very intensive surgeries. So types of operating rooms here can also include general surgery operating rooms, an emergency or a trauma room, or an endoscopy space. So the goal here for the operating room is to always ensure that while this patient is in a sensitive state, we can protect them from germs being transferred in the airstream. So in order to build up this protection and this protective barrier, we're going to aim to maintain a positive pressurization. So we're always going to ensure that air transfer is moving from the operating room out into the corridor. So in order to do this, we're always going to ensure we have more supply air coming into the space compared to exhaust air leaving the space. Additional requirements you may see here in the operating room includes a room pressure monitor outside the space to give us a visual and audible alarming on how that room condition is being maintained. And then you may also see an additional larger operating room monitor inside the space to give the hospital staff, the surgical team, an understanding on where some of those key variables are, like temperature, air change rate, and pressurization. The last application we're going to cover here is compounding pharmacies. Compounding pharmacies are going to be the spaces where specifically the hazardous chemicals and drugs are being mixed, such as chemotherapy drugs, while also ensuring that this is mixed in a clean environment. The goal here is to minimize as much as possible any potential spoiling of those drugs while they're being mixed due to less clean air getting involved or potentially unsanitary conditions in that type of compounding pharmacy. So there are a couple of different spaces that you may see in a compounding pharmacy. This can include a sterile, non-sterile, hazardous, or a non-hazardous space. Now these can all be mixed and matched depending on the requirement of the space. So you may see sterile hazardous compounding pharmacies, non-sterile non-hazardous compounding pharmacies, and vice versa in that sense. So in this case, we're only going to cover a couple of these key types of compounding pharmacies. So the first one we're going to cover here is non-sterile compounding pharmacies. These are spaces involved in creating the medication in a clean environment, but there's not the strict requirements of maintaining that space to be completely free of all microorganisms. So usually these types of spaces, we're going to be working on potential drugs that are administered topically. So in this case, you can see here, you may also have a type of additional exhaust device like a biosafety cabinet in that non-sterile compounding space. You may also see you're going to have pressure monitoring inside the pharmacy to give visual indication to those pharmacy staff as well. Next, we have sterile compounding pharmacies. So again, sterile compounding pharmacies, we now have the requirement of ensuring the space is free from all microorganisms. So in this case, what it means is we may again still have our biosafety cabinet or a CPEC machine, which is the containment primary engineering control device, which is ensuring that we're preventing the worker from being contaminated from these microorganisms as they're mixing these drugs. So the goal here for our biosafety cabinet or our CPEC device is minimizing that exposure to hazardous drugs for both the worker and the environment. The last type of space you may see here in a compounding pharmacy that we'll be covering today is the shared compounding pharmacy. So shared compounding pharmacies here include a little bit more of an integration level. So you may see you have a sterile and or non-sterile hazardous space, and then you may also have a non-hazardous sterile space depending on that functionality needed in that pharmacy. The key item to note here is typically shared compounding pharmacies are going to have a cascading pressure relationship. What this means is the pressure set points as required for these pharmacies are being measured in reference to each other. So a fluctuating room pressure in your anteroom may cause pressure stability issues in your additional adjoining spaces. Now, we strongly recommend in compounding pharmacy applications to utilize pressure monitoring at each doorway to ensure that we can properly isolate and properly monitor that key pressure relationship for that space. Additionally, door contact switches are strongly recommended for these types of application to ensure that if a door is left open, we can alarm and encourage users to keep those doors closed in order to not disrupt that room pressurization in this pharmacy. So now that we've covered in high level the types of applications we may need to utilize this room pressurization strategy, we're now going to go ahead and talk about what type of control methods we can use to maintain that pressurization. So the first control method we're going to talk about here is volumetric offset control. This is also commonly known as flow offset control. The strategy for volumetric offset control is to maintain a constant CFM offset between our total supply air coming into a space and our total exhaust air leaving a space. This is going to be regardless of the room mode changing as your space goes heating into cooling or in other different conditions. So as you can see here on the chart on the right side, you can see that the blue line is our total supply air coming into the space. The red line is our total exhaust air leaving the space. And as you can see here, over time, as that space goes from occupied to unoccupied, or as it goes from heating to deadband into cooling, we want to ensure we're maintaining a fixed constant offset over time. So by being able to maintain that fixed constant offset, we're able to build up the pressurization in the space without having to essentially directly measure and control for that room pressurization. ANSI Z9.5 states that flow offset control, again, is going to be the most commonly applied approach for most critical spaces. You can use room pressure sensors and door contact switches for applications for volumetric offset, but these will all be utilized for monitoring the space further, not controlling to that volumetric offset. So as you can see here, if we have 1,000 CFM of supply coming into a room and 1,100 CFM of exhaust leaving a room, that's going to leave us with a room offset of about -100 CFM. If a door is opened, in this case, we're not reacting to the changes happening in that space. We're still maintaining that same fixed offset in the space. Now, the second strategy we can utilize for maintaining that room pressurization in these critical spaces is direct pressure control. Direct pressure control allows us to do airflow adjustments for our total supply and total exhaust based on live readings of that room pressure. So now we're taking live readings of the room pressurization and we're controlling our air exhaust valves or our air valves, both on the supply and exhaust side, to maintain that constant set point. So what you're going to see in these types of application is your actual room offset may fluctuate over time, but the goal is your pressure set point is being maintained at a fixed constant over time. In order to enable this strategy, you will require to have a room pressure sensor to take live readings of your pressurization and door contact switches in order to monitor when that door is open. Now, ANSI Z9.5 states that it is impractical to maintain your differential pressure across an open door, since most HVAC applications, you're not designing your room pressurization for the door being open. When that door is open, it introduces a very large hole into your space, and it's going to be very difficult to maintain that pressure set point while it's open. ASHRAE 170 also states that, again, short-term excursions from required pressure relationships shall be allowed while the door is open or moving in that case. So in this exact same scenario, we have 1,000 CFM of supply coming into our space, 1,100 CFM of exhaust leaving our space. This gives us roughly a room pressurization of -0.02 inches water column. Now, in this sense, if the door is open, we're no longer maintaining our pressure set point, but if we're implying and utilizing our door contact switches to monitor that door state, once that door is open, we're going to freeze the valves in place and then continue controlling once that door closes again. So with that, those are going to be our two main strategies that we can utilize and deploy for controlling our room pressurization in a space. Now, once you've identified which control strategy you would like to utilize, we can now go ahead and cover what other design considerations you want to review. So thermal considerations are going to be a very big driving factor for us in these spaces. We want to ensure that our critical space is properly conditioned based off of the thermal loads. In a lab application, you may have a large number of additional equipment generating thermal loads that may need to be covered. On the other end, with healthcare, that might have a variety of different types of equipment that needs to be considered. So with that, again, ASHRAE outlines in chapter 16 a very simple equation that I'm sure a lot of you are familiar with on how to determine and calculate airflow rates based off of these thermal loads. So instead of covering this in detail, what we're going to cover instead is the different strategies we have available for controlling temperature in these spaces. The first type of control method we're going to cover is our staged temperature control. So this is a temperature control method where we have a reheat or a cooling coil where it's going to operate from fully closed at 0% all the way to 100% fully open before any additional airflow is added into the space. Now, typically a staged temperature control approach will be more efficient since we can focus on maintaining temperature set point with water or electricity before needing to add any additional airflow. We can try to control temperature with one technology first before introducing a second one. Due to this approach, stage temperature control will be more stable since we only have one device we need to worry about performing the majority of temperature control. But because it's only one device operating at once, it may be a little bit slower. So if you do have applications where you have a large number of thermal equipment that can be turned on and off at once, or if you have a space that's facing potentially exterior windows where you can get a large swing in thermal loads when the sun is shining, you may want to consider a synchronous temperature control approach. So in this sense, we are now controlling our reheat coil between fully closed 0% to 100% fully open, while at the same time, we're adding additional airflow into the space. So because we're utilizing two devices, both the reheat and cooling coil and airflow at the same time to control for temperature, you can see very fast approaches to maintain set point. But now that we have a faster approach to maintain, a faster way to maintain set point, we may need to dial down our control loop a little bit here during commissioning to avoid any extreme overshoot or undershoot tendencies. Now, ideally with synchronous temperature control, it can be a faster approach since we're either adding more hot and cold air while increasing the airflow set point at the same time. We will want to make sure that we dial in that approach during commissioning. So the last form of temperature control approach we're going to cover here is going to be our room temperature control with DAT limits, or discharge air temperature limits. The goal here now is, instead of just controlling our room temperature by taking a reading from our room thermostat and modulating our airflow and cooling coil, we are instead going to try to maintain a constant discharge air temperature from our supply airflow. The idea here is the room temperature will tell our discharge air temperature set point target to increase or decrease based off the demand. Because we're controlling the room temperature based off our supply discharge temperature, we can actually now set limits on how hot we want that supply air temperature to be, or how cold we want that supply temperature to be, in order to minimize some of that overshoot undershoot. So the essence here is this form of temperature control should be extremely stable. It may be a little bit slower to react, but it will really help minimize any potential swings or instabilities you may see. So now that we've considered some of the strategies in order to maintain the thermal temperature in a space, we can now start talking about some of the strategies we can incorporate to control our airflow in and out of the space. So what type of airflow control devices can we see utilized in these critical spaces? Now, due to the nature of these critical spaces having such an impact on safety of the users in the space or potentially patients, we're going to want to ensure that we're introducing and utilizing air valve that can help control airflow accurately. So in this sense, the two approaches we have are utilizing an electronically pressure independent air valve or a mechanically pressure independent air valve. So with an electronically pressure independent air valve, the actuator on this valve will typically move and adjust when there's changes in your airflow target and if there's changes in your duct pressure. So the example here could be terminal boxes or high accuracy terminal units. On the other end here though, we also have mechanically pressure independent air valves. So these are air valves where your actuator only moves when there's a change in your airflow target, not when there's a change in your duct pressure. In this case, the example is going to be a Venturi valve. In essence though, if you're picking your air valve technology, the key thing you're going to want to ensure is that you're selecting an air valve technology that ensures it can control airflow accurately to ideally plus or minus 5% of your airflow target. So to shed a little bit more detail into this, the first one we're going to talk about is our electronic independence air valve, more specifically the high accuracy terminal unit. So our high accuracy terminal unit, as the name entails, is going to be a higher accuracy version of your classic VAV box. So in this sense, it's going to be a terminal unit type technology that allows us to control airflow within 5%. So in this sense, typically with your high accuracy terminal units, we're taking direct airflow measurements. This could be through static pressure readings. This can be through an orifice plate reading. It depends on the technology you're selecting. You're typically going to see a 10-to-1 turndown ratio utilized. Typically, high accuracy terminal units won't require any straight inlet or outlet duct run requirements. And then lastly, generally, there should be some resistance to contamination. So in this example you see here, the high accuracy terminal unit we're showing, it has the static pressure ports it utilizes for airflow readings behind the ports facing downstream of your airflow direction. So the benefit of this is it gives us some natural protection from lint, dust, and other contaminants that can get into your airstream and into the duct. So on the other end, we have our mechanically pressure independent air valve, which is going to be a Venturi valve. So the benefit of a Venturi valve is that there is no sensors inside the airstream measuring flow directly. It's utilizing an electronic feedback based off of the lever arm position to give us an understanding of what flow set point the valve is going through. So because the valve has no sensors inside the airstream, it means that we don't require any inlet and outlet duct run requirements. And additionally, it will give us some protection to dust, lint, dandruff, because there's no sensors inside your airstream. Typically, your Venturi valve will have a larger turndown ratio compared to your higher accuracy terminal units, mainly for the fact that it's not measuring flow directly, it's utilizing that positional flow feedback via a high accuracy potentiometer. So to really put into perspective, we need to understand how can we apply these Venturi valves or high accuracy terminal units in application. So typically in application, you're going to roughly have three types of requirements for your air valve technology. Is the valve constant volume? Does the valve need to operate at a 2 position? Or do you require a fully variable air volume type valve? So if you are considering an application that requires a constant air volume valve, the Venturi valve, since it's mechanically pressure independent, can be mechanically set from factory to operate at that set point. The benefit here is you don't require a controller, you don't require an actuator to control the valve, meaning that you can get a valve to mechanically control to that constant set point. On the opposite end here, you do have your high accuracy terminal unit. Since your high accuracy terminal unit needs to be able to measure airflow in order to control to that constant volume, you are still going to require to have an actuator and a controller in order to do a constant volume application with the high accuracy terminal unit. On the other end, if you have a 2-position air valve application, with a Venturi valve, we can operate and utilize a 2-position actuator with a relay feedback to control the valve between a min set point and a maximum set point. So in this case, you are going to have a 2-position actuator on your Venturi valve, but you don't require the need of a controller. On the opposite end again though, because your high accuracy terminal unit needs to be able to measure airflow in order to control to a set point, you will still need to have a controller and an actuator in order to achieve a 2-position type operation. So the last type of application you might see here is going to be your variable volume applications for your air valve devices. So with both the Venturi valve and the high accuracy terminal unit, we are essentially going to need a controller and an actuator in order to modulate the air valve to the variety of different set points needed. So in this case, for both valves, you're going to see it come with a controls enclosure and an actuator in order to achieve that variable volume control. So now that we understand the strategies of how we can implement pressurization control through either offset or pressure control, we understand the different types of thermal controls we can utilize to maintain temperature in a space, and we understand what type of valve technologies we may want to consider in order to achieve that airflow and temperature control. We can now consider how we monitor and how we visually display that room pressurization. So for this last section, we're mainly going to be considering what is the difference in application if you need room pressure measurement, room pressure monitoring, or room pressure control utilized. So there are going to be, of course, some key differences in each type of application or strategy. If you are utilizing a room pressure measurement strategy, you typically only are going to need to have a pressure transducer located in that space to give us a physical reading and monitoring of that room pressurization. If you want to include local potential monitoring of that room pressure reading, then we're going to want to also introduce a type of display, a monitor that can allow us to visually display and report what's being measured. And the last strategy we have here is if we're actually trying to control to a pressure set point and we want to utilize room pressure control, we're also going to have to factor in the controller in that system. We need a device to take in that reading and enact that change on the system. Having the monitor in that space for room pressure control is optional, but in most situations, you may still want to have that monitor there for local visualization. So the first thing we're going to cover here is room pressure measurement. So again, room pressure measurement is the strategy where we want a device dedicated to take that reading for us in order to give a visual reading of that quantity. So here we have an example application of a sterile compounding space. In each of these spaces, we want to ensure that we're maintaining the proper pressure relationships between the spaces. So between the anteroom to our corridor, we're going to try to maintain a positive 0.02 inches water column of pressure. In our non-hazardous space, we're going to want to make sure that it's more positive compared to our anteroom, so roughly 0.03 inches of pressure. And then we want our hazardous room to be negatively pressurized in reference to our anteroom. So in this case, we're going to want it to be monitored and controlled to about negative 0.03 inches of pressure. Now, as we talked about earlier, this type of pressure monitoring relationship would be called a cascade pressure relationship because we're measuring both our non-hazardous and our hazardous space to the reference anteroom. If we wanted to change this and not have to have this cascade pressure relationship, we can locate our pressure transducers to all reference a common reference such as the corridor. If this is a strategy you want to implement though, you will have to change the magnitude that's being monitored for both the hazardous and non-hazardous space. So in this case, our hazardous room will now need to be monitored and controlled to a negative 0.01 inches of pressure in reference to the corridor, which still ensures that the hazardous room is at least a negative 0.03 inches of pressure in reference to our ante. Likewise, our non-hazardous space here is now going to be monitored at least positive 0.05 inches of pressure, which ensures that it's at least a 0.03 inches of pressure greater in the positive direction compared to our anteroom. So with that being covered, let's say we now want to implement a monitoring approach in this type of application. So we want to introduce a type of display that can give us a visual and potentially audible alarming of that room pressurization reading. So again, putting a monitoring device in an application like a critical space is important because it can give us a live visual indication. There are a number of different strategies you can utilize for these types of applications. So for monitoring, you can have a ball and tube in the wall, or you can have a digital display. Of course, nowadays, it's way more common to have a digital display than utilizing something a little bit more mechanical like a ball and tube sensor. Additionally, you may also want to consider the differences of having a local monitor in that space versus having a remote monitor at, let's say, a nurse's station or a director's office. And then lastly, having off-site monitoring through your building management system integration. So with any type of monitoring devices that you're going to be utilizing in this type of space, things you're going to want to consider as additional options are going to be audible alarming, integration with your building automation system, custom graphics to show key details, and things like that. So if we're looking at the same application for compound and pharmacy, in this sense, we have 3 pressure transducers utilized, both monitoring the pressures between and in reference to our anteroom. In this case, since we have 3 pressure transducers, we can utilize 3 pressure monitors. Each of these pressure monitors are monitoring a single zone, a single space, and giving you monitoring on that indication, on those changes happening. So in this type of application, as you walk into the pharmacy, you have 1 display outside the room. As you're inside the anteroom, you can see on both displays what the readings are of those spaces. Now, this isn't a requirement. Another strategy you can look at is potentially minimizing how many pressure monitoring displays you have. So in this sense, we have 3 pressure transducers, but instead we're going to have 1 pressure monitor, and that 1 pressure monitor is going to reference all 3 pressure zones for us. So instead, we now have essentially 1 place to go to see that pressure reading for all spaces. Now, if you do want to implement a strategy like this, you still most likely want to have a display outside the pharmacy to give us some sort of indication before we come into the space if it's safe to operate and be in. So in this sense, you may also want to have a pressure monitoring display outside the space. Now, this isn't necessarily a requirement. We can also have a larger backnet display that we can utilize instead. So if you want to minimize how many types of displays you need to have, you can have a 3 pressure monitoring display inside the room, and then you can have a larger display outside that shows you all of the key details that you want to be monitoring before entering into this pharmacy and mixing your drugs. So the last type of application we're going to cover here is room pressure control type applications. So these again is when we now want to have a device to measure what that pressurization is, and we also want to enact a change on that system. We want our air valves to react in order to maintain a set point for us. Again, having a monitor for this type of application is optional, but in most cases you may still want to have that monitor. So here we have an example wiring diagram for isolation room. We start with our pressure monitor. So we have a room pressure measurement sensor that's now giving live readings to our monitor in that space. That package by itself will now give us local pressure monitoring and flexibility there. But in order to enact the change and allow our air valves to control to a set point, we are going to want to have a signal go between our pressure display and our air valve in order for our air valves to now control based off that reading. So if that reading, let's say, is higher than our set point, our air valves can now react to that change, and vice versa. If your pressure reading is lower than your set point, the valves can now react in order to maintain the ideal state in that space. Now, of course, having that monitor in that space isn't a requirement. If you wanted to just have a pressure measurement, but then still control based off of that, in this case, we have a pressure transducer directly connected to our air valve. That's going to give us that room pressure measurement and live reading. We're going to have a backnet communication here, so at least the building management system can monitor the live readings from that pressure sensor. And then now our air valve technologies can now control based off of that set point. So now they can react to different changes in that space. So with that covers what we wanted to discuss here in today's webinar. So just to do a quick summary for you guys here. So we first started the presentation by just explaining and talking about some of those key applications in critical spaces like pharmacies, isolation rooms, operating rooms, and laboratories. And we also covered the basics of room pressurization and how potential leakage in your room will affect your pressurization based off of the magnitude. So with that here, we talked about the 2 main types of controls you may see in room pressure that you can implement for room pressurization. You have your volumetric offset control, which is the most commonly used across all applications. But the other strategy you have here is direct pressure control. This can be utilized in healthcare and in pharmacy types of application. We also covered the different types of temperature control. We covered the differences between stage temperature control, which is when our reheat coil will modulate before any additional airflow is added into the space. We have synchronous temperature control. This is where our reheat or coolant coil will modulate at the same time additional airflow is added to our space. And the last option we have here is room temperature control with DAT limits or discharge air temperature limits. This is where, again, our reheat coil is going to modulate in order to maintain a set point for our supply air temperature entering into that room. Additionally, we talked about the different types of airflow control devices you can select depending on your application and project requirements. Again, with your high accuracy terminal units, you are taking live airflow readings. It's going to be electronically pressure independent with the usage of an actuator controller. And then we also have a Venturi valve, which is airflow metering that valve. It's mechanically pressure independent. It's able to control airflow without taking those live airflow readings directly in the airstream. And then we finish off the presentation here talking about the differences between room pressure measurement, room pressure monitoring, and control. So room pressure measurement will require a sensor in the space to give us readings. Room pressure monitoring will require us to have a pressure sensor and some sort of display, either be a local monitor, front-end monitoring, things like that. And then lastly, we have room pressure control. This is going to require at least a pressure sensor giving readings to a controller in order for us to modulate the airflow set point or the airflow targets. Again, a display is optional, but typically it's going to be utilized.